Brebner. I'm the technology evangelist at Instaclustr. I'm based in Canberra in Australia. So thanks for joining. This presentation is about building zero-code streaming data pipelines using open source technologies. So let's get into it. Just a bit of background. The Instaclustr managed platform. This is a complete ecosystem to support mission-critical open source big data applications. It covers a whole bunch of different use cases, different technologies, and we provide it on different cloud platforms as well, with a lot of enterprise features that are missing in the bare bones open source technologies. So this talk focuses on an IoT use case. Kafka and Kafka Connect as a sort of a common technology, and then two options. Option one is Elasticsearch or OpenSearch and Kibana. Option two is PostgreSQL and Apache Superset. And pipes. So some pipes can be quite puzzling. I saw these blue ones everywhere in Berlin a few years ago and wondered what they were for. I wondered, perhaps given the history of German beverages, whether they were for transporting beer. I actually believe there are beer pipelines, but I'm pretty sure these aren't for beer. Pipes can be quite boring as well. They can just be straight and run off into the distance. Pipes can be fun and I guess potentially dangerous in some cases. Pipes and integration can be complicated. This is the pipe system for a rocket engine, which is something you don't want to go wrong at the wrong moment. So I guess the meta question behind this talk is building a robust, scalable, zero-code open source data pipeline a pipe dream? Well, let's find out. Here's an overview of the talk. We're going to have a look at the story first, the two options, option one, option two, how you monitor them, the scalability results, and some final conclusions at the end. So what's the story? Well, it was probably well over a year ago now that I was watching the online Kafka Summit, and one of the talks was quite interesting. It was explaining how the American CDC department had built a Kafka COVID-19 specific pipeline in under 30 days. I thought that was a fairly impressive achievement. And some of our consultants at the same time actually built a demonstration application using similar technology, but public climate change data via REST connectors running on Docker, which was also quite an interesting example, I thought. So I thought, well, why don't we try and use some streaming REST public data sources and deploy the whole application running on Instaclustr managed services. So I had to look for some public streaming REST APIs with easy to use JSON data format, complete data, interesting domain, and not too political or apocalyptic. It was quite tricky at the time, but I did finally find something which satisfied my requirements. This is the USA tidal data. It's from the National Oceanic and Atmospheric Administration. And did you know that tides follow the lunar day rather than the Earth day? I always knew tides were a bit funny. They always change, the high and low tides change time every day. And the reason for this is that the lunar day is actually 24 hours and 50 minutes long rather than just 24 hours long. So that's the type of data that we're going to be using for our example. The NOAA website has a lot of data, a lot of interesting information. Here is an example of the location of the tidal sensors that they provide and how many are in each sort of aggregate location. You can drill down. You can say, well, let's have a look perhaps at the northernmost location and see what's there. And if you drill down into that, you can see a picture of what's there, the station itself, some metadata about the location, and then also some of the sensor information itself that's available and some of the actual raw data graphed over time, which is pretty cool. And more important for our application, there's really good documentation about the API. So it explains how to use the API, how to request data from different locations, how to get different metrics, different amounts of data, and what the example JSON data that comes back will look like as well. So here's a REST example. It's showing how you specify the station ID, the data type and the datum, which in this case is the water level and mean sea level. And then you can request just the latest data point that's available and ask for it to be in JSON format. And if it all works, then you get an example that looks like that, which has two main components: the metadata field, which includes the ID, the name, lat long, location, and the data field, which includes a timestamp and the actual value that is returned. So let's start the pipeline using the Noah REST API for the data sources. What else do we need to build the pipeline? Well, we need Kafka Connect. So this is a common technology I'm going to be using for both of the options. It's a distributed solution to integrate Kafka with other heterogeneous data sources and stores. It provides connectors in either source or sink flavors to handle the details of the particular integrations. So the source connectors get data from source systems and put them into a Kafka topic. The sink connectors get the data from the Kafka topic and send it off to whatever target sink systems you have in mind. Why would you use Kafka Connect? Well, it promises zero code integration, high availability, and elastic scaling independent of the Kafka clusters themselves. So option one in more detail, this is using Elasticsearch plus Kibana. Elasticsearch is for the scalable search of indexed documents. Kibana is for visualization and analysis. I'm using Open Distro for Elasticsearch, which is Apache 2 licensed. So how do we spin up a cluster? Well, I use the Instaclustr console. Just a few clicks on the screen to provision Kafka and Kafka Connect clusters, and then they're ready to use. So now we have Kafka and Kafka Connect clusters running. Next, we need to find a REST connector. And for a connector that's not provided as a default in our managed service, you have to deploy it to an AWS S3 bucket, tell the Connect cluster which bucket it's in, and configure the connector and run it. So there's a few steps there. The instructions are on our website for what we call the BYO or custom connectors. So here's an example. We've got a REST source connector configuration, which includes details like the connector name, the class, the URL, and the topic. So there's a fair bit of data that you need in these sort of configurations, and they're all different across different connector types and whoever developed the connector as well. So this polls every 10 minutes. It writes the result to the Kafka topic, and I picked 5 sensors to use more or less at random. So there are 5 connector instances running. So now we have tidal data coming into the tides topic. What next? Well, next we have to provision the target sink systems, in our case Elasticsearch and Kibana clusters. So again, I'm using the managed service that we have for that, and there's just a screenshot of the console. And then we have to configure the default Elasticsearch sink connector to send the data to Elasticsearch. So luckily we have one that we provide as part of our managed service, so I just used that one to see how it went. Here's an example of the configuration. You need the connector name, class, index, and topic. The Elasticsearch index is created with default mappings if it doesn't already exist. Great, so it's all working, well, sort of. So tide data is arriving in the tides index, but Noah data is in JSON format, and Elasticsearch is JSON native, so that's all good. However, in the default index mappings, everything is a string. It turns out to graph anything as a time series by name, you need a custom mapping. So here's an example of custom mapping in Elasticsearch. We need to specify that T is a date, V is a double, and name is a keyword. And you just run that curl command with that configuration data against the Elasticsearch cluster, and that creates a custom mapping for you. Oh, and reindexing. So every time you change an Elasticsearch index mapping, you have to delete the index and index all the data again. So where do you get the data from? Well, there's 2 options. turns out that using a Kafka sync connector, the data is already in the Kafka topic, which is great. So you can just replay it, or you can use the Elasticsearch reindex operation. So the hard part is over. Now you can start Kibana with, again, a single click on our managed service console. And there's the Kibana homepage. And then there's a few more steps before you can actually visualize the data. So here are the initial visualization steps. One, you have to create an index pattern, which gets the data from Elasticsearch. You have to create the particular visualization to create the particular graph type that you want. And then you have to configure it so that it's going to display the data you've got correctly in the way that you want. So here's an example of a successful chart that I created. It shows time on the x-axis versus the average tide level relative to average level in meters for the 5 sample stations that I picked. So something is obviously working correctly. We're getting data in to Kafka. The data is going from Kafka to Elasticsearch, and we're able to display it in Kibana, and it looks sort of interesting. What can you see in the data? Well, first of all, we can see what we were expecting. It's the lunar day, which is a 24-hour, 50-minute period between high tides. So that's obviously working correctly. You can also see something that I didn't necessarily expect as well, which is sort of interesting. So some locations actually have quite big tidal ranges. So Nia Bay, for example, has about a 3-meter tidal range, I think. And the tidal range is just the difference between the high tide and the low tide. So some of them have a lot bigger tidal range than others. So evidently tide range varies depending on a whole bunch of things, including the moon, the sun, local geography, and even the weather. So this map shows globally where some of the bigger tidal ranges are in the darker, redder regions of the map. Nia Bay is actually sort of at the edge of one of those regions. So even some of the other sensor locations would have had even probably bigger tidal range that I hadn't picked to display. Australia's biggest tide is actually here at this location. It's quite famous. Evidently, tides of over 11 meters go through 2 narrow passes, creating a very popular tourist attraction known as the horizontal waterfalls in the Kimberley region of Australia. I haven't been there yet. One day when all the lockdown stuff's over, perhaps I'll get to travel and have a look at it. So next we want to have a map to show the sensor locations to understand perhaps a bit more about where the big tidal ranges are occurring. So here we have a map, but there are no geo points in the data, as it turns out. So nothing's actually being displayed by default on the map. So there's a few more steps we need to solve the mapping problem. Elasticsearch doesn't recognize separate lat-long fields as what it calls geo points. So you have to add an Elasticsearch ingest pipeline to pre-process documents before they are indexed, which, we need to reindex the data again. The 3 steps are add the geopoint field to the index mapping, create Elasticsearch ingest pipeline to construct the new field, and then add this as the default ingest pipeline to the index. And here's an example of how to do that. This shows adding a new location field for the geopoint data type to the mapping in the index. Second step is to create the new ingest pipeline, which constructs the new location geopoint string from the existing lat-long fields. And finally, you have to add location pipe as the default pipeline to the index. And all being well, we've now got a pipeline transforming the raw data and adding the geopoint location data in Elasticsearch. Now we want to visualize this data. Here are some steps. We use an existing index pattern, so we don't have to create one from scratch. You create the visualization, and then you configure the settings to display the data properly. And all being well, this is what you end up with. This is a map showing the sensor locations and the minimum values over the last week. So the size of the circle is proportional to the minimum value of the tides. You can also add your own custom web map service layer. This gives you a lot more flexibility in providing your own custom maps and more detailed maps, although there's something slightly strange about this one that I found. I believe there is supposed to be a landmass between the USA and Alaska. I don't know quite exactly what's normally there, but something does seem to be missing, doesn't it? But what can go wrong? Well, there's a couple of things with this example that can go wrong. First of all, the REST call can return JSON error messages, but this isn't treated as an error, so it's just sent as a normal message to the tides topic and therefore to Elasticsearch and to the index. The second problem is to do with the gateway that's evidently used on the Noah side. So sometimes it can actually just return an HTTP error message, which basically means that the sensor is unavailable and no data was available at that point in time. But HTTP isn't, again, treated as an error message, so it's also sent through to the tides topic. Unfortunately, this causes the Elastic Sync connector to fail. So it tries to read the HTTP error message and doesn't like HTTP, so it fails to the fail state. Luckily, I'd configured everything so that the exceptions were viewable in the Kafka Connect logs topic. Otherwise, I would have been pretty stuck trying to work out what was going on at this point. The Kafka Connect framework in general is actually quite robust. It automatically restarts workers if they are killed, but I was quite surprised to find that it didn't automatically restart them if they fail. So that's something to watch out for. What are some solutions? Well, one solution is if the connectors support one of the Kafka improvements, KIP 298 error handling in Connect, then you can configure them to ignore input errors, and then the errors are sent to a dead letter topic. But one of the problems then is, where can we find connectors with more robust error handling? Well, in the Australian Outback, you occasionally come across signs like this one, which warn you about jumping animals, very large guinea pig-like animals, and guess what? Camels. Apache Camel is one source of connectors. Australia has the most wild camels in the world, and Apache Camel turns out to have the most Kafka connectors as well, about 346 different connectors. Apache Camel is quite a mature project. It's been around for about 10 years. It's focused on integration of systems. It has lots of components to integrate everything with everything. But where do they get so many Kafka connectors from? So Camel meets Kafka. Camel Kafka connector. It's a bit of a mouthful, a tongue twister, that one. It's a new sub-project which enables Camel components to be used as Kafka Connect connectors. How does it do this? It uses automatic generation of connectors from Camel components. There are source and/or sync connectors depending on which Camel components are available. The Kafka Connect configurations contain a mixture of the Kafka Connect and the Camel configuration, however. So you really need to read the documentation for the Camel component and the Camel Kafka connector as well. And then there's a fair amount of trial and error to find all the required fields and get them working. But let's take one for a test ride and see how well it goes. So here's an example of a Camel Kafka or Elasticsearch sync connector configuration for error tolerance. It's pretty much similar to some of the other examples with a few Camel specific things. So you have to have something called a cluster name. That's a convention in Camel for endpoints. You have to specify the dead letter, queue, and the level of error tolerance. And we're going to try all and see what happens for this example. So now we have a robust handling of HTTP errors. The connector does actually keep running quite happily and ignores the HTTP errors. So that's quite an improvement. I tried to configure it to handle JSON errors as well. Couldn't get it to do that. I also tried solving that problem on the Elasticsearch side using something which is sort of like schema validation, but not really. There's a setting which enables you to turn strict validation on which does reject the message on the Elasticsearch side, but unfortunately the sync connector actually still fails when it gets the error message, when it gets the exception from Elasticsearch, so that wasn't entirely successful at that point. Let's have a look at the second option. This is one that I've only just quite recently done. It involves PostgreSQL and Apache Superset. Why did I think this was interesting? Well, two reasons: curiosity and opportunity. Apache Superset looked like an interesting alternative to Kibana for doing the visualization of data, but it does only work with SQL databases, so I couldn't try it with Elasticsearch. On the other hand, PostgreSQL is an open source SQL database, and it was on our managed services roadmap. And at the time I was doing this work a few months ago, available as an internal preview. It's now actually available as an initial public preview. PostgreSQL also has excellent JSON support. There's a JSON-B column type, which is an indexed JSON binary format, and it enables complex and fast JSON queries. So it looks like quite a good match. Let's see how it goes. So the next problem I had was finding some open source Kafka Connect PostgreSQL sync connectors. Are there lots of choices? No, there was only one that I could find, which wasn't really supported anymore. Then I thought, well, how about JDBC sync connectors? PostgreSQL supports JDBC, and that means there are actually multiple potential JDBC connectors available. So I did an evaluation of quite a few. However, most of them assume that you have an explicit schema as part of the payload. They assume you have a simple flat JSON data object, and most assume that you want to insert elements into multiple columns in Postgres database. What was the solution? Basically, I needed a schemaless approach. So what did I do? I hacked the IBM JDBC sync connector code to read a JSON Kafka record value, create a PostgreSQL table with two columns, an auto-incrementing ID for the primary key, and a JSON-B column with a GIN index, and then insert the JSON object into that column. How robust was this solution? PostgreSQL itself rejects invalid JSON. So the HTTP error messages, for example, were successfully rejected by Postgres. And you can also configure Postgres to have constraints. So I could check if JSON has data and metadata fields, and therefore reject the JSON error message, which had neither. So that actually worked pretty well. The next thing I wanted to have a look at was Apache Superset. I had a couple of questions around whether this was going to work or not. The first one was how would I even deploy it? So up until now, everything I'd tried was part of our managed service offering. Apache Superset is not at this point. I tried a few different ways of getting it running, and the simplest turned out to be just running it on my laptop in Docker. So that worked okay eventually. The next question I had was, will it connect to PostgreSQL okay? I thought I may have had to have spent some time with that, but it was pretty trivial, basically. And it turns out that PostgreSQL is actually used as the default metadata store for Superset anyway, so that was easy. So the more difficult question was, can it access and then chart JSON-B PostgreSQL data types? Well, after quite a bit of effort, I discovered the answer to this was yes, but you have to use something called virtual data sets. You need to use PostgreSQL JSON-B operators, cast, and functions to create a virtual data set with separate columns. So here's an example of creating a virtual data set for the Noah title data. It has a whole bunch of things in it to extract data from the JSON-B column, and then turn those into separate columns, which I can then chart in Superset. So the next thing you have to do is pick a visualization type in Superset. So there's a lot of visualization types, probably almost too many. It's quite difficult to know which is the right one. So for picking ones to do mapping, I picked one called Mapbox, which seemed like a sensible name. And it's mainly designed, I think, for showing clusters of location data. However, it did work okay. The SQL free chart builder worked okay on my virtual data set as input, and I could get some data appearing. As a prerequisite to getting the maps working, you do have to get and configure a Mapbox token for any of the geospatial visualizations to work in Superset. That's straightforward enough. There are lots of visualization types, more than 50, and lots of detailed geospatial charts that are called deck.gl. So here's an example showing some of the NOAA sea level trends. It's a deck.gl scatter plot. Size and color are sea level trends in millimeters per year. It shows that some locations will flood earlier than others in the next 50 to 100 years. Maybe not a good idea to buy property in those locations. I did cheat slightly for this example. I actually used the NOAA sea level trend data, but I could have done the analysis in Superset to produce the trends as well. So will the system scale? Let's scale up and open the floodgates and see what happens. To find out how well it's scaling, you need to know what to measure. There are lots of metrics in all these different systems, so finding the right ones and understanding how they all relate to each other is quite critical. The relevant metrics were collected with Prometheus from the Instaclustr monitoring API across multiple systems. So the boxes in green there showed the ones that I eventually picked. They're mainly from Kafka Connect cluster, the Kafka cluster, and the Elasticsearch cluster as well. And then if you display them all on a single Grafana dashboard, then you can actually see what's going on really well because they're all related to each other. So the goal is to increase the number of tasks and throughput, but keep the lag down in the system. So let's race Elasticsearch versus PostgreSQL. Definitely, this is a camel race using robot jockeys on the top. Strange, but true. Let's have a look at the infrastructure we used. Across both technology options, the Postgres pipeline on the left and the Elasticsearch pipeline on the right, there's a very similar number of cores and therefore total cost in terms of the infrastructure. What else can we see? The Kafka Connect cluster has the most cores, followed by either Postgres or Elasticsearch. And the Kafka cluster is actually quite lightweight by comparison. Focusing purely on inserts a second, this is our first attempt results. So this is using both of the results using Kafka sync connectors. It's sort of an apples to apples comparison, although as you can see that one apple is a lot bigger than the other apple basically. So PostgreSQL result was a lot better than Elasticsearch, which was surprising and unexpected, and slightly inexplicable initially as well. So we've got around about 42,000 inserts a second into Postgres, and only about 1,800 into Elasticsearch. So there's a whole bunch of configuration information there if you want to try and replicate this. One of the important things, of course, with Kafka is to make sure you have sufficient but not too many petitions. One of the issues I encountered on Postgres as well was trying to optimize the number of database connections. That's sort of the same concurrency mechanism in Postgres compared to Kafka. Or on Elasticsearch as well, you have to have sufficient shards, but again, not too many. So the number of shards really should probably be equal to the number of nodes you've got in your Elasticsearch cluster. That seems to work okay. So that was the first lot of results. The second lot of results is my second attempt in the Mythbusters methodology. Basically, you make the result that you want, or you make it work. And I knew I wanted to increase the throughput in Elasticsearch, and I knew that one way of doing that was to use the bulk API, and that turned out to work okay. And we ended up with two results that were pretty comparable, but using quite different approaches in the long run. So more on apples to oranges comparison as well. So I sort of cheated a bit by using the Elasticsearch Python client with 50 threads and the bulk API. So I bypassed the Kafka Connect cluster altogether in this case. Some caveats as a result. So the bulk API was used and I was not using Kafka Connect. The Postgres master server CPU plateaued at about 50% CPU, whereas I was able to push the Elasticsearch CPU up to about 80%. So there's still some capacity on the Postgres server as well, I think, that's not being utilized yet. However, Elasticsearch does scale horizontally with more nodes and shards, so you will get more throughput with Elasticsearch purely by adding more nodes. On the other hand, it was with identical JSON data and very similar size and costing clusters. So just some conclusions to finish up. First of all, looking at Kafka Connect, which was the common technology. Kafka Connect enabled heterogeneous source sync zero code integration of streaming JSON data, but some custom mappings and SQL was required for the sync systems. It has good scalability and throughput, aided by custom monitoring. To scale, you increase the number of connected tasks, Kafka partitions, and sync system resources, but it is the most resource-intensive cluster in the stack. It has two useful Kafka superpowers, which is the ability to buffer spiky loads and the ability to replay data. So data is persistent and read many times, which is quite handy when you're trying to do reindexing or reuse the same data from multiple sync systems. Open source Kafka connectors are of varying quality, functionality, robustness, and performance. So you need to evaluate and test with valid and invalid data. Robustness is a function of connectors and the sync systems. It required hacking to work correctly with complex schemaless JSON data. And you really need to test the performance and scalability. So comparing the two different options, starting with Elasticsearch versus Postgres. I've got a bit of a table here, just trying to summarize some of the main pros and cons. On the Elasticsearch side, the sync connectors did work, but you really need to use the bulk API. I couldn't find an open source one that did use the bulk API, but in theory, you could modify one or find one that worked okay. On the PostgreSQL side, I did have to hack these sync connectors to work in the way that I wanted with schemaless JSON data, but it did work eventually. PostgreSQL, both of the error types that I encountered worked well and were handled. You don't have to have any custom mappings on the ingest side of Postgres, it just works. In terms of resources and throughput, they're both pretty comparable. And of course, the final difference may come down to horizontal scalability, which Elasticsearch supports, but PostgreSQL doesn't out of the box that I'm aware of. Looking at Kibana versus Apache Superset in terms of the data visualization, well, certainly the Kibana option was the easiest for me to deploy. It was just part of our managed service. Superset needed custom JSONB SQL queries to get at the JSONB data. In terms of support for databases, Kibana only works with Elasticsearch. Superset will work with many SQL databases, and I believe Elasticsearch, but I haven't tried that yet. There are a lot more chart types in Superset, but again, you need to spend some time picking and testing them out to find one that will actually work the way you expect and display the data in the way that you want. So that's it from me. Why don't you try us out, Instaclustr.com. There's a whole bunch of managed services we provide for all of these technologies. The public preview of managed PostgreSQL now is available, and just go to our website and click on the free trial button, and you can try any of these out and try and build your own pipeline or other application as well. Thanks very much for your time, and if you want some more information, check out my blogs, Instaclustr.com, Paul Brebner. There's a multi-part, I think it's up to 10 parts pipeline series now that this talk is based on, and links to the GitHub, which has the example configurations and the working connectors that I used as well. So you can replicate all of this and more just using that as a starting point and your own imagination. So thank you very much. Hope the talk was interesting, and please ask questions, I guess, on the chat afterwards, or send me some messages via my LinkedIn would also work as well, I guess. So thank you very much.